The magnitude of the magnetic field in a region of space is changing as B equal 2 times e to the power minus 5t, where B, magnetic field, is in Tesla and time t is in seconds. A coil of radius r equal 2.5 centimeters is placed in the magnetic field as shown below. Find the induced EMF in the coil at time t equal 3 seconds and the direction of the induced current. Let's start by writing down what the problem gives us. We know that the radius of the coil is 2.5 centimeters. The magnetic field changes with time as 2 times e to the power minus 5t. We need to find the induced EMF in the coil, and for that we are going to use Faraday's law that allows us to calculate the induced EMF as minus the rate of change of flux with time, d phi by dt. For that, we need to find the flux. So we start by calculating the flux using the definition of flux. Flux equals integral of the dot product between the magnetic field B and the area dA. In evaluating this integral, we need to figure out first what changes. Does the magnetic field change over the area? Well, the magnetic field changes over time, but it does not change over the area. Does the area through which we calculate the flux change? No, it does not. The coil has a radius that is fixed, 2.5 centimeters, and therefore the area through which we have magnetic field does not change. How about the angle between the magnetic field and the area vector? Well, the direction of the coil in the magnetic field does not change, so therefore the angle is constant. Knowing all this, let's evaluate the integral. Flux equals integral of the dot product between the magnetic field B and the area vector dA. And we are going to write first the dot product. Remember, the dot product is equal to integral of the magnitude of the first vector, which is the magnetic field, multiplied by the magnitude of the second vector, which is the element of area dA, multiplied by the cosine between them. Well, the magnetic field comes out of the page, and the area element is also oriented out of the page because, according to the convention, the area element is always perpendicular to the area and away from it, towards your eyes. Since cosine of 0 is 1, we can write that the flux equals integral of the magnetic field B multiplied by the element of area dA. Now let's replace the magnetic field with the expression given for it. The magnetic field is 2 times e to minus 5t. And because this quantity does not change over the area, it comes out of the integral. And we have flux equals 2 times e to minus 5t multiplied by integral of dA. Well, integral of dA is nothing else than A, area. The same way integral of dx is x. In this case, the area of the coil is a circle, and we can calculate the area of the circle as pi times the radius of the circle squared. We have found an expression for the flux, and as you can see from this expression, the flux changes in time. Now, the next step is to find the induced EMF. The induced EMF is minus the rate of change of flux with time. So that would be minus d by dt of 2 pi r squared multiplied by e to minus 5t. 2 pi r squared is a constant, comes out of the derivative, and we have that the EMF equals minus 2 pi r squared d by dt of e to minus 5t. The first derivative of e to any power is nothing else than that power, which in this case is minus 5, multiplied by e to minus 5t. So we have minus 2 pi r squared minus 5 multiplied by e to minus 5t. And all we have left is to replace the given values in this expression. We need to find the induced EMF in the coil at time t equal 3 seconds. So we will replace the time with 3 seconds. And that gives us minus 2 pi. The radius of the coil is 2.5 centimeters or 0.025 meters. Don't forget to square it. Multiplied by minus 5 multiplied by e to the power minus 5 times, and the time t is 3 seconds. That gives us a value of 6 times 10 to minus 9 volts for the induced EMF. As you can see, we obtained a positive value for the EMF, and that means that the induced current will flow counterclockwise.